Hello, can everyone hear me?
Yes,
Yes,
ma'am.
ma'am.
Okay, thank you. So I guess you have been in contact with your class representatives, and we will have an assignment which I will upload by end of this week, and a small quiz on Saturday, 5th September from 11 to 1 p.m. It will be a really short one with short questions, so you don't need to worry. It will only be on basic concepts. Okay. Yeah, so I just wanted to tell you that in my lectures, I try to go a bit into more details and a little more advanced topics. And maybe the assignments will be more or less at the same level, but the quizzes will be much more simpler. So don't worry about it, okay? And some things are, of course, topics which I touch on. There, you are not really familiar with all the concepts there. You will understand them better after Professor Pal has taken his modules, and I have also taught at the end. So when you come back for it before the to these lectures before the end SEM, you will understand much better. So don't get too worried if you don't understand at this point. And I will not ask questions from those things which I think you will not fully understand at the moment. Of course, those of you who do know the advanced topics and can understand, you are welcome to go into more details and ask me questions, no problem. Okay? So I see that we have 71 people so far, but it's really increasing rapidly. So I will just wait for 2 more minutes before starting the class. Okay. In the meanwhile, if any of you have any questions from last class? No? Okay.
Ma'am, I have a question.
Yes?
Okay, I guess I'm not going to be able to switch my earphone.
I can't hear you very well.
Ma'am, I had a question regarding that calculation part of Wien's displacement law from Planck's law.
Yes.
I couldn't understand one part where you had assumed hc by lambda kt as x, and you wrote iteration, something about iteration, that x to the power n equals to x to the power n plus 1 equals to 5 into 1 minus e to the power minus x and to the power n, something like that. Like, I couldn't understand the notations.
Okay. I suppose you are not familiar with the concept of iterations. So I also got the same question from someone else as well. The thing is, an iteration basically means you start with a guess value and you frame your equation to have the x equal to some function of x. And then when you evaluate the function, you use this guess value and you obtain an updated x value from the equation. Then you feed back this new x value into the function and evaluate the function with the new value of x. Okay, and then you keep repeating this till you have reached a desired accuracy. So I have put up an example on WeLearn actually in response to the question of one other student. Okay, you can look at it if you want to. It will
Okay,
be clear.
ma'am.
I used a numerical example there.
Okay, and there was one more thing
Yeah.
about like I was reading the Atkins, and they have used a term called density of states. Instead of naming it as energy spectral density, they have used a term called density of states. Like, yeah, instead of using spectral energy density.
What is in Atkins right now? But I think by density of states they would mean the n nu that I have used. So the number of so the combinations of n1, n2, and n3 which satisfy the the conditions of the box length being multiples of the wavelength by 2. So I guess the density of states is not the energy density, most probably. But
No, actually they have named it like that. The energy density they have symbolized with some italicized E, and then dE equals to rho into d mu, and the rho they have used instead of the rho they have told that it's density of states, and with that they have used the formula which we used for spectral energy density, like this is 8 pi 8c. That thing I couldn't, like, they are writing the same equation for density of states as we are writing from spectral energy density. So it would be like, and I also have problem in like to relate spectral energy density with energy, like what it actually is. Spectral energy density, what do we mean by that?
okay, no, so the last part I can tell you, that is, spectral energy density is the energy emitted in a certain frequency range. So from nu to nu plus d nu. And the total energy is for all the frequencies at that temperature. But okay,
Multiplied by volume, and then multiplied by volume, maybe like spectral energy density, like we integrate it with respect.
energy density is per unit volume, yes.
Okay, per unit volume and per unit
This is
frequency.
theoretical construct, so you have so for it to compare with experiment, you have to have per unit volume. And the total energy will also be per unit volume, I think, because the box is the theoretical construct.
And you explained in the last class about non-conductive walls of a the cavity which we are using as black body.
Yeah.
There was this one thing, and you told that the reflected waves would probably not be generated in response to the electric field of radiation, and it would be a little difficult to create those radiations as well, considering if the cavity is completely non-conductive.
Yes.
Yes. So, and but in the PDF which you had sent, it was written something like currents would not generate if, like, in response to the electric field of incoming radiation. That is the reason why the walls should be conductive.
Both are true actually. So if you have radiation inside the cavity, then if this radiation does not create currents in the walls of the black body, then this reflection of radiation inside the cavity will not occur. Also, if the body is insulating totally, then you will not even be able to generate the radiation. So both are true, actually.
Okay, ma'am. Thank you.
Sangeeta,
Yeah.
Sangeeta, just one question.
Yes.
In case I'm not there till the end of the class, and
Yes.
if you feel that it is appropriate, then you can announce the next class from Tuesday. I will come in.
Okay, I think I thought about it. I think you can take from Tuesday, and we can have the doubt clearing class after the test. Maybe that would be better.
Okay, okay, that is fine. So that you can tell them, tell the students.
Okay,
So that's
okay.
what I was telling. Depending on what you decide, so they should also. Huh?
Yeah, I
So-
can announce it right now. I think we are now
Okay.
at full strength.
Then it is fine. Then I will also prepare accordingly, and that's fine. Okay.
Yes.
So you
yes.
continue.
So
Sorry.
then, okay. So
Sorry.
you,
Okay. Okay. You continue. I may not be there till the end.
yeah, sure.
So thank you.
Okay, thank you. So then that is decided. So everyone in the class, so now you know that from next Tuesday, Professor Pal will start his module and he will continue for however many classes he needs to do the second module, okay? And please let others know also, those who are not attending this class or cannot attend, okay? Although it doesn't matter, I guess the Google Meet link will remain the same. So you can use the same link. Okay. So now I will proceed with today's class. So today's class is basically on wave-particle duality. So this is something that fascinates anyone who starts studying quantum mechanics. But the whole problem arises from the fact that we're used to thinking of new things in terms of old things. And we have been so familiar with distinguishing matter from radiation or waves from particles that when we were faced with things which behaved as both, it confused us to no end. So it's the same problem as gender. So since we are so used to labeling things male and female, people have a problem accepting transgenders and gay and all these problems, okay? But if you did not have any sort of label, then there would be no problem. If you just felt everything was fluid. And this was the same thing here. But since it was science and somehow things get more easily accepted in science when presented with evidence, people have come to accept quantum behavior and have accepted that things can behave both as waves and particles. But still, when you start out, it confuses us. So I will try to put forward my point of view on how I understand this, but I feel there are many, many schools of thought, and for some people it's even philosophical. So you are free to think of it as you like, but the evidence remains the same. Okay, so you have to accept the evidence. So first we look at the evidence. So when you do a Young's double slit experiment with light, then you get an interference pattern. And the interference pattern coming from superposition of waves has become it is the hallmark of wave behavior. When you do the same with particles, you expect something like this, where you just have particles around the position of the slit, not an interference pattern as in the first figure. However, when you do a Young's double slit experiment with electrons, with sufficiently small slits, you also get an interference pattern, which is just clear evidence that the electrons are somehow interfering with each other and forming an interference pattern. On the other hand, as we studied last class, you cannot explain photoelectric effect and Compton effect without assuming that that somehow light travels in indivisible packets of energy, and they can transfer momentum to matter. And this is clearly what.
Ma'am,
yeah?
ma'am, you aren't presenting. I'm not sure if you think you are. But...
You did not. I am sorry about that. Yes, so can you see this now, the slide?
Yes, ma'am.
Yeah. So this is the first slide that I was showing you, sorry. So this is the first figure where you see the interference pattern of light. Then with particles, you expect just two lines at the position of the slits. And in the third figure, you see the interference pattern for electrons. Okay. On the right, we have the photoelectric effect and the Compton effect, which we studied about last class. Okay. Now the problem, so this was the evidence showing that particles could form interference patterns and light could transfer momentum to matter and be indivisible somehow. Okay, so this is particle behavior. And this meant that we had to expand our concept of waves and particles. And you can summarize this by saying that the dual properties of particles and waves are found for all particles, where I'm generalizing the term particles to being massless like photons or having a mass like electrons. So we are reclassifying things. We are saying that there are some fundamental particles, and they can be massless like photons or have mass like electrons, and these show both wave and particle behavior. Now, what was the first evidence of this? So this was an interesting experiment by Davison and Gerber. So what they were trying to do was they were trying to study the surface of a nickel crystal by shining an electron beam on it. So they generated the electron beam by heating a tungsten filament, which is this one, and then they accelerated it with the accelerating potential, and then they shone it on the nickel target and measured the reflected electron beam with a movable detector for various angles of theta. So what they expected was that they would get some sort of intensity distribution of the electron current in some continuous fashion. But what they observed was that at some angles, they got a sudden spike in the electron current. Okay, and for certain accelerating voltages, they experimented with many accelerating voltages. These peaks became more prominent. Okay, this was fine. They could not explain it, but then something even more remarkable happened. There was some damage to their nickel target, and then they heated the nickel crystal to reform it so that they could use it. And what happened was that the nickel target, which was that they were using, it was polymorphic, so it had different crystal structures in it. But after they heated it and cooled it, they got a pure crystal with very, very nice parallel atomic planes. And then suddenly their peaks, the peaks that they were obtaining, they became even more clear. And then they got even more confused. But what happened was that around this time, they attended a conference where quantum behavior of particles and the wave nature of particles, which was still theoretical, this was being discussed. And some of their older experiments were being used as proof of this wave behavior of matter. So then they went back. So they went back to their lab and they redid this carefully. Now with the aim of demonstrating the wave behavior of particles. And then they could explain this very well. So what they tried was to use Bragg's law, which is the diffraction law for radiation. And when they applied Bragg's law to find the wavelength of the electrons, and D being the, it is normally the gap between this in the diffraction rating, but here it was the interplanar gap in the nickel crystal, and they obtained the wavelength of the electron to be 0.165 nanometer. The de Broglie relation, which was proposed earlier as a hypothesis, this gave, which is lambda is equal to h by p, p being the momentum of the electrons, this gave the wavelength of the electron to be 0.167 nanometer. Now, this was very good agreement, and it was almost conclusive proof that electrons can act as waves and produce a diffraction pattern, these peaks in the graph. So the graphs on the right, that was what they obtained for various voltages. Okay. And this peak at 54 volts and 50-degree angle, this was the most prominent peak corresponding to n equal to 1. Okay. Sorry. Yeah. This was corresponding to n equal to 1, this peak over here. Later on, of course, other particles have also been shown to undergo diffraction, neutrons, atoms, and most recently even fullerenes. So what you need basically is the diffraction grating you are using to have a slit width comparable to the wavelength of the matter wave of the particle you are studying. And since these wavelengths are so small, this wave behavior of particles had escaped detection for so long, because manufacturing a diffraction grating with this sort of gap slit width is very, very difficult. So Davis and Germer were lucky in using actually atomic planes as the diffraction grating, and later on the same principle has been used for other particles. Okay. Now we go back to the hypothesis that de Broglie had proposed. This was before the experiment, okay? So you had said that we don't distinguish waves and particles really. So, so Einstein had said that waves have particle character, which means that photons are actually indivisible packets of energy, and their momentum is related to their wavelength, which is the second equation here, P is equal to h by lambda. De Broglie turned it on its head and said, what if we use the same relation, but given a momentum for a particle, we say that it has a wavelength. Okay, and here, so P can be mass into velocity, the momentum of the particle, a moving particle, and that will give a wavelength. And although these two equations, you're just changing the variable, they imply very, very distinct things. So this is the wave nature of particles, and the second equation is particle nature of wave. And it unifies the two, actually. So what you can say is generalize all small, so when you have small particles and when you have low intensity waves, or when you're dealing with phenomena involving only single photon interactions, then you sort of see the particle nature of wave or the wave nature of particles. Okay, and then you can generalize them both to be mass with mass and without mass quantum particles. Okay, and then when you go to larger and larger combinations of massless particles, then they behave largely as waves. And when you go to large combinations of particles with mass, they behave largely as conventional objects or matter as we know it. So this puts particles and waves on the same footing. And also, when you just think of particles in motion or just a wave, like a free thing, when you're not considering an interaction, then you can think of it as relative to the dimension of the object. So when the wavelength of a particle is very much less than its dimension, then it becomes insignificant and you observe conventional particle behavior or matter behavior. And when the wavelength is proportional to the dimension, you get wave behavior. Okay. So there are two categories. So one is when you are not considering an interaction, then the dimension is the relevant thing to know what behavior this quantum object will show. And when it is interacting, then the dimension of what it is interacting with and the nature of the interaction tells us whether it will show wave nature or particle nature. Okay. Now, from a quantum point of view now, how do you explain this? Okay. So how the explanation that I feel most comfortable with, and I guess it is the most widely accepted at the moment, is that everything is a wave packet. What is a wave packet? A wave packet is a short burst or envelope of localized wave action that travels as a unit. So it is like a little pulse that is traveling. And how to generate this pulse? You can think of this pulse as a superposition of very many waves with phases and amplitudes. So if you recall your physics related to sound, you know that every wave has a phase. So the crest corresponds to a certain angle, the trough corresponds to a different angle, etc. And this angle is called the phase. And the amplitude, which is the height of the crests and the troughs. And they interfere. So, and when they interfere constructively over only a small region and destructively elsewhere, you generate a wave packet. Okay? And in case of quantum waves, you can consider each component of the wave function to be solutions of a wave equation. And the superposition of this generates the state, and this state is the wave packet. Okay, so this is particular to quantum. So the concept of wave packet is very, very common in sound physics and everything. But in quantum physics, the relevant concept is that the component waves are solutions of a wave equation, the quantum wave equation, and the superimposition generates the wave packet. Okay, and depending on the wave equation, the wave packet's profile, so what it looks like, it may remain constant, as in the figure over here, or it may change with time. So when it remains constant, you say there is no dispersion, or it may change when it's propagating, and then you say there is dispersion. Okay. So let's look at this figure a bit more carefully. So this rectangular block here, that is one of let's say, the peak of one of the components. So all the components are not shown. The blue is the resultant, and one of the peaks of the components is the rectangle. And you see that that is also propagating slowly with time, and the wave packet is also moving. But the two are moving at different speeds. So if you follow, say, the 1, 2, 3, 4, 5, 6, so the central peak of the resultant, that is the 6th peak, that has easily overtaken the one of the components. So actually you can have combinations. So here the one component is slower than the resultant. You can have all combinations. You can also have a wave packet which does not move, and that would be a localized particle. So to understand that, we distinguish the velocities of these two waves, and these are called phase velocity and group velocity. So the velocity of each component wave is called the phase velocity, and the velocity of the resultant wave, the envelope of the waves, is called the group velocity. Okay. And from classical wave theory itself, it is the group velocity which carries the energy of the resultant. Okay. And this is important in the sense that for matter waves, then, this group velocity, which comes from the velocity, which is the velocity of the resultant coming from all the components which are solutions of the quantum equation. So the resultant velocity is the classical velocity of the particle. Okay. So, and then once you relate the quantum behavior to the classical velocity, you can identify the energy and momentum of the particle with the relativistic energy and the relativistic momentum mu. So mu is the velocity, classical velocity, respectively. And from de Broglie relation, you get this whole set of equations. Okay. So this is the wave equation. So lambda into frequency is equal to angular velocity into a wave constant. And you use the relations, the de Broglie relations, and you come to the relation lambda nu equal to c by beta, where beta is defined as the classical velocity by the velocity of light. And from this, the most relevant conclusion is that when you have a massless particle, then it moves with the velocity c. So beta becomes 1, and you have lambda nu equal to c. So you get back the normal equation for light. That wavelength into frequency is equal to velocity. So this is sort of how you go from a wave function representation of a particle to its to the classical concept of a particle moving in space. Okay. Now, to understand these phase velocity, group velocity, and the superimposition, I think you should definitely watch this video, because then they can show you an animation of how this happens. I tried to embed this in my presentation, but I was not successful. So please do watch this link. Okay, don't skip this one.
Ma'am, you are telling about a component wave, and solutions to the component wave form the wave equation. So, are the component waves, each component wave, a single wave packet, or it's not? Like, I just wanted to ask that.
No, the resultant is the wave packet. So the component waves have this infinite spread. They are the wave functions, and then the superimposition that gives you the wave. Like all the solutions together.
Okay, so the envelope of waves, like superposition of each component wave, results into the small wave packet.
Yes, yes.
Okay, thank you.
In the video, they show it really nicely. So I really recommend that you watch it. And fine. So this was about matter waves and how you relate a quantum solution to a classical particle in motion.
Ma'am?
Yeah?
Ma'am, when this wave packet is localized, that's when it forms a particle.
Yes.
Alright. Okay.
Yeah. So if you have the more localized a wave packet is, the more particle-like that particle is. So next we come to light. So here we were talking about particles being waves. Now waves being particles. Now light has confused people for even longer than the wave behavior of matter, because people have been studying light for a very, very long time. In fact, the first concept by Newton was that light was a particle. He said corpuscles. Okay. And then afterwards, there was the discovery of interference and diffraction, and people shifted to light being a wave. And then again, with Einstein, we shifted back to a particle, but then we accepted that it could be both a wave and a particle. Okay. And I took two tables of the internet which tried to sort of help you explain whether it's a wave or a particle, or what behavior is wave-like and what is particle-like. But you can easily see that they contradict each other. So one table says that reflection and refraction can be explained in terms of particles, and one says it's not. So basically, there is still a lot of confusion. What is considered a hallmark of wave behavior is interference, and what is considered a hallmark of particle behavior is the photoelectric effect and the Compton effect. But other than that, there are multiple explanations, but there are problems with both explanations. So my take on this is that you should just accept that light is a quantum object. Okay, you don't need to classify its interactions as wave or particle in any particular situation. It is quantum in all situations. That is my favorite explanation. And it is, of course, possible that you quantize the electromagnetic field in terms of, and then the field also has discrete energy parcels or photons. Okay, and the photons you consider as massless particles of definite energy, momentum, and spin. It is a quantum massless particle. Okay, and it follows a different statistics from matter particles like electrons, which have half integral spin, but you can ignore that part. I just mention it now so that you can come back later. Okay, the slide is complete, but you don't need to understand it at the moment. But what I want to say is that you can also have a quantum equation for the photon, and you can have a wave function for it, and this will faithfully reproduce all the phenomena that you know about light. Okay, and you will study the harmonic oscillator model in greater detail somewhere at the end of the course, close to the end of the course. And then when you look at the quantum model for the harmonic oscillator, it is very close to the quantum model for light. So you will get an idea there. Okay, so you don't need to really classify light. That is my understanding. You can just accept that it will show quantum behavior, and if you do use the most accurate quantum model for it, you will be able to explain most phenomena. However, I should mention here that it is not a completely solved problem yet. There are still problems with having an accurate model, quantum model for light, and it continues to be an active field of research. Okay, and it is a really complicated topic actually. Okay, now of course, once I put electrons and photons more or less on the same footing and say everything can be treated as quantum, the question may arise in your minds, well, then are they just the same? Well, they're not quite the same. There are some very fundamental differences, such as electrons have mass, photons are massless. That is something you have to keep remembering. Photons move at the speed of light. Electrons always move at a speed lower than the speed of light. Electrons have charge. Now, this is something we have not addressed so far, but that is a very important difference. that they have charge and photons do not. Electrons cannot be absorbed or emitted like photons can be. And why is that? That is because destroying an electron or creating one out of nothing would violate the conservation of charge. So the matter-energy conversion is known, that you can convert energy to matter, but you cannot. But we cannot violate the conservation of charge as of yet. We don't know how to do that. Okay, so absorbing an electron simply and creating one out of nothing, that is not possible. So that was what we had about what I had about wave-particle duality. So you just sort of need to live with it and come to accept it. Then we come to the Heisenberg uncertainty principle, and this is related a lot with the wave packet picture of particles. So in school or even at the beginning of college, I was presented with the uncertainty principle as in terms of measurement, and that confused me to no end. So the statement that we are used to is that you cannot measure momentum and position accurately, like exactly for a quantum system. That you cannot do it simultaneously. And this is a very confusing statement. So what does that mean? My teacher then explained it by saying that when you use a photon to hit a particle to find out its position or its momentum, it disturbs the particle. Okay, and naturally I always thought, okay, but this is like an experimental problem. I don't necessarily need to hit something with a photon. What if I could devise some other way of knowing? Then what would happen? But actually, this is a redundant question. You don't. The Heisenberg's uncertainty principle has nothing to do with trying to find out something. Okay, so what if I wasn't trying to find out position and momentum? Then does the particle have a definite position and momentum? This is a valid question, right? I mean, no one needs to be looking at something for it to have something. So then later on, I figured out and I read and whatever, that you can have an alternative understanding of the Heisenberg uncertainty principle, and that is what I want to present today. That is in terms of wave packets. So, like we spoke about a few minutes before, a wave packet becomes increasingly localized with the addition of many waves. But when you add many waves of different momenta, it increases the uncertainty in the measurement of the momentum. So when you have a large range of momentum, it means that the intrinsic range of the momentum increases when you have more and more waves of different momentum. So a wave packet, if you want it to have a very well-defined position, so if you want it to be like a straight peak with no uncertainty, you will need an infinite number of waves with an infinite range of momentum. Okay, so which means it does not have any definite momentum whatsoever. No range, no finite range. Okay. And when you do that, then the component waves will be moving with a very diverse range of speeds, and they will become decoherent very easily. So they would just move at different speeds, overtake each other, and the wave packet would be destroyed. Okay. Conversely, if you construct a wave packet with a very definite momentum, so then you have, let's say, only one component wave function, then it will travel a long distance and not disperse. But this will have an infinite spread in the first place. So that is what light is. It is infinitely extended in space, and it has a definite wavelength, and this wavelength does not change. So it has a definite momentum coming from its wavelength. So these are the two extremes, and which means that if you consider a particle to be a wave packet, then the uncertainty principle is a given. There is no way you can avoid it. It has nothing to do with trying to shine light on it and find out its position or find out its momentum. Okay. So now I go into a little more mathematics about the derivation of the high uncertainty principle. I think most of you will not be familiar with the terms in this slide.
Ma'am,
Yeah.
you have said that when the wave packet is the resultant of various range of momentum of different waves, its position is certain, but
Yeah.
and it if it is reverse, the is its momentum will be certain, but actually a particle is the combination of the uh, components of different momentum, or is the combination of the different components having same momentum?
They are the particle represented by a wave packet is a combination of waves of different momentum. Because unless if they are of same momentum, then you can't have this constructive and destructive interference at different points. If you want it to be localized, that is, for it to become a wave packet, you need the components to have different velocities and different momentum. And when you're talking about the classical momentum of the particle, that is the momentum of the resultant, that comes from the group velocity. That is the resulting momentum in a way. And here, when I'm talking about the range of momentum, it is the momentum of the component waves. And you need them to be different to form a wave packet in the first place. Okay. So when you combine waves of the same momentum, then you have basically a resultant wave. You will not have a wave packet. When you find the wave function solutions for a particle, you will get a range of components of different momentum. Okay. Is that clear? Or
No, I am asking that if the particle is the combination of the waves of many momentums, or just waves of same momentum.
Many momentum.
If it okay.
Yeah, many momentum, but they superimpose to give you one resultant momentum, and that is the momentum of the particle.
Which is not certain.
Which is not certain. No.
Which is uncertain.
Which is uncertain. Because it's a dynamic. The superposition is dynamic. Since you need the wave packet to move, it's not a static superimposition. That you superimpose the components to form a wave, and then this moves. It's not like that, right? The components are moving, so the imposed wave function is also changing with time, and consequently it's moving. I think it will become clear when you watch the video. I would have really liked to show you the video, but I don't think there is time anymore. I will just finish up quickly. Okay, I have just 2 more slides. And if I have time, then I will show you the video. Fine. Okay. So this is how I like to think of the Heisenberg uncertainty principle. Now the mathematics of deriving it. This is for those of you who are maybe a bit more familiar with the maths here. So a Fourier transform, put simply, is representing one function in a certain variable, let's say psi x, in terms of, you convert this to a function of another related variable. Okay, to put it very, very simply. there are mathematical expressions, and you will encounter it in lots of fields of physics, and eventually you will all know about it. I'm not sure how much you know right now, but I just want to mention it. So that is where the derivation comes from, and the variables that you transform between are called conjugate variables. In case of wave functions, the relevant variables are the position x and the momentum p. Okay, and it can be shown mathematically that a non-zero function and its Fourier transform cannot be sharply localized. So when you have a wave function in x and you transform it to a wave function in momentum, since they are Fourier transforms of each other, you cannot sharply localize both. So that is another way of understanding mathematically the uncertainty principle, that it is mathematically impossible. And from this concept, you can show that the standard deviation of x and p, it obeys this bound, that the product of the two standard deviations is always more than equal to h cross by 2. H cross is called the reduced Planck's constant, that is h by 2 pi. Okay, and this is called the Kennard bound. So that is how it is derived, this bound. So the uncertainty you can understand conceptually, but why it is this figure, you need to go into the mathematics of it. But you don't need to know the derivation really. But you do need to know the implication. So the two errors have an inverse relationship. And since to derive this, you only require that the two functions, that is the wave function in terms of momentum and the wave function in terms of position, are Fourier transforms of each other. The uncertainty principle holds for any pair of conjugate variables. So if you couch your problem in different variables and you can show that you have a pair which are conjugate variables, you can always have an uncertainty principle for it. Okay. And when you have studied the next module and you are aware of what operators are and what commutators are and what these symbols are, I want the slide to be complete, so I put this up here. You have a general uncertainty principle, which is that the standard, so the variance, square of the standard deviation of two observables, Q and R, have this bound. So this uncertainty is always greater than equal to 1 by 2 I is the imaginary number, is the average of the expectation value, as it is called in quantum terminology, of the commutator of the two operators. The square of that, okay. And based on this, you can derive the uncertainty principle for different pairs of conjugate variables. This is the general expression. So the other relevant uncertainty principle is the energy time uncertainty principle, which is very similar, looks very similar to the position momentum uncertainty. But, okay, and how you normally explain it is that delta E is the uncertainty in the energy of a state and delta T is the lifetime of the state. But there is a fundamental difference here from the position momentum uncertainty. Since there is no operator for time, you cannot use this generalized uncertainty to derive this relation. Okay, so there is an alternative way of deriving this relation, and I have put it up on VLearn in handwritten notes, but I would like to come back to it after you know about operators and how to handle wave functions, etc. Okay, so at some point after the second module, I will come back to this and show you the derivation for this result. For now, you can just be aware that you have different uncertainty principles, and the two most important are the position momentum uncertainty and the energy time uncertainty. Okay, so I will stop here, and since there is some time, I will try to show you this video of phase velocity and group velocity.
You right. Network security is important for any organization. You know, you should take this online ethical hacking course.
Suppose we add several waves together to create a new wave. If we change the amplitudes of the waves, the resultant wave also changes. The waves can have different wavelengths. The bottom wave has a slightly different wavelength than the other two. As we move the two other waves, notice how the sum of all the waves changes. The resultant pattern moves at a different speed than the original waves. We refer to the speed of each original wave as the phase velocity. We refer to the speed of the resultant pattern as the group velocity. When we have a wave describing a quantum particle, it's the group velocity that determines the velocity of the particle. Any wave function can be thought of as the sum of waves of many different wavelengths. For a quantum particle with mass, such as an electron, the waves with a shorter wavelength have a faster phase velocity. For classical water waves on the surface of an ocean, the waves with a shorter wavelength have a slower phase velocity. When different wavelengths have different phase velocities, we can have dispersion, where the waveform has a sharp peak at one moment in time, but is dispersed at another moment in time. On the other hand, if all the different wavelengths have the exact same phase velocity, then the pattern can stay constant, and the group velocity will be equal to the phase velocity. Examples of waves where all the different wavelengths have the same phase velocity are electromagnetic waves through a vacuum and waves on an ideal string. If we have waves with the same amplitude and speed, but moving in opposite directions, then we produce what we refer to as a standing wave. Much more information about waves is available in the video.
Okay, so that was the video. I will stop presenting now. Okay, so I have stopped presenting. I'm also stopping the recording.